Okay, everyone. So this is your first day back, and probably a lot of happy faces because people did phenomenally well on this exam. I was hesitant to post the average and the median because I thought people who did really well would feel like, oh, I'm only average, right? But you guys did phenomenally well, and the average was 89, I think, and the median was something like 91 or 92. So this is super high. I know that that means that for some of you, you don't have a chance to really shine. If you're up at the top, maybe it was, there's not much discrimination up there. But I'm just really happy because it's, you didn't have any formula sheets, and you had a lot of concepts, and a lot of you are coming from different backgrounds. So I'm very happy that at least we're all starting off well, except, there's some people who didn't do so well. And I think those people, if you want to go over your exam with me, that would be great. Right now, I just want everybody to, since this is a first exam, I want to make sure that everybody understands how things are graded. So we'll just spend 5 minutes now, and then I'll let you out early so that those of you who have individual questions can ask them. All right. Now, did anybody not find their exam? Raise their hand. You don't have your exam. We'll see me right after class, and we'll look for it, okay? So you see these numbers right here? If you have all zeros here, that's great. It's the number you got wrong. If you got, this is how many points you got off. So all zeros is good here. Now, I just want, this is posted on our website right here on our exam schedule. Just click there and you'll get it. So you can all look at this. But I just want you to look at this thing called continued error. If you haven't been in Stat 100, you might not have seen this before. In problems where continuing errors you don't keep getting points marked wrong. So for example, if you got this wrong, the standard error here, then of course you're going to get this wrong. So these continued errors say continued error from certain parts. So we'll take off in the beginning, but we won't continue to deduct throughout the problem because, a careless error at the beginning of a problem shouldn't be like ruin your entire grade, whereas a careless error at the end of the problem would only cost you a few points. We don't think that's fair, so we follow your logic through. It's a lot of work for us, so you could have the entire page wrong but not miss that many points if you just had an error at the beginning. That's really true on page 2. So, and a little bit on page 3. There was a little bit of continued error. We will say where it is on the key, so you can look at that. And that's basically the exam. And if you have any questions and want me to go over it on your own individual exam, I'll let you out somewhat early and stay and you can ask them, okay? It's just people did so well, I don't think there's a need to go over it. All right? Any objections, any questions, comments, anything? All right. Then let's get back to the notes then. Okay, so what are we doing? Remember what we were doing here. We're doing this analysis of variance. All right? But we're just doing it right now for simple regression where we don't have to do it. For simple linear regression, we're just looking at what we're testing is whether the slope in our simple model, simple meaning just one x, predicting one y. For example, this question. How well does homework predict finals in this sample? And the null is that it doesn't do anything. It does there's no correlation, that the slope is 0 in the whole population. We just happen to see this signal, this effect in our sample due to just random variation, sampling error. You know, every time you take a sample, you're going to get a different correlation. So even if there's nothing in the population, you could easily, depending on your sample size, you're more or less likely to get far away from that. Let's say there's nothing going on. So the idea is that we just have, I'll just draw it over here. Let's say we just have this little scatter plot here where we have homework predicting finals. And this is the population. In the population, let's say there's 2,000 students. So there's 2,000 points in here. And the null hypothesis says inside this population, there's no correlation. There's no correlation. Rho, our Greek letter, R for the population, is 0. That's the null. That's equivalent to saying that our slope, the slope for homework, no matter what the homework score is, it doesn't make any difference. There's a flat regression equation. So it doesn't, whatever you get on your homework, our best prediction for the final is what? The average. We can't for all the finals. We might as well predict the average. It doesn't, homework, it would be as if this was like height. Height's not a good predictor for final, or weight or something like that. So that's the idea. That's the null. And then we say there's 2,000 points in here. Well, imagine if we just took out 3 or 4 points. We could easily get 3 or 4 points that happen to have a positive correlation of 0.4 or a negative correlation of negative 0.4, right? Or higher if we just have a few points. But with, we have a sample size here of what? 107 points. So that's going to be a lot less likely to happen. So really all we need is this 100 and the n and this sample correlation to get our t statistic like we did before, or our z. So that's what we did before. Just to refresh your memory, on the next page we show you this was the t statistic. This was, and it just depended on R and N. This was our t statistic. And when we had a large enough sample size, we said the t is going to converge to the z, and so we said we could use this as well. They're very similar, and you can see in the structure, when n is big, these two will be very close together. So now, what we're saying is, well, if we square those two, we'll get, if we square the t, we'll get the f, and if we square the z, we get the chi-squared. And these statistics, this f and the chi-squared, are the way that we're going to be doing analysis of variance. They're based on the sum of squared deviations. There's not, we can't boil it down to a single signed number. So for simple regression, there we have we could choose either one. If we have a small sample and the assumptions are met, we can use these. And if the larger sample and the assumptions are met, we can use these. So we have our choice, okay? So the structure of the analysis of variance is looking at sums of squared deviations, because think about it. Right now we have just one x predicting one x predicting one y. But we're going to add another x. So imagine another x coming up out of here, right? We'll be in 3D very shortly. And even 4D, 5D. We're going to add more and more predictors. And then what we're going to be looking at is the sum of squared deviations, because we have to look at the whole pattern to see if there's any pattern at all. And we can't say whether it's positive or negative, because think about it, some of the slopes could be positive, some could be negative. They could cancel each other out unless we ignore the signs by squaring and look at the size of the effect. And that's what the F analysis of variance does. It compares the mean square of your model to the mean square of your error. So let's go through it with this, and we can do it by showing you this chart. But since we're given this R, we can do it also just a very simple way by using this formula. So why don't we do both? All right, so we're going to use this analysis of variance to test the null that rho in the population, that R in the population is equal to 0 against, now look at this alternative right here. It's always an analysis of variance, it's always an inequality, because we're looking at the sum of squared deviations, and our test statistic can only be positive. So we can't determine whether it's a negative correlation or a positive correlation. We can just see whether we're just testing whether there's a correlation, which is the same thing we do when we do a two-sided t-test or z-test. All right? There's no direction here. So we assume the null, and we compute how likely would it be to get this sample R of 0.4. How likely would that be just by the luck of the draw? That's the idea, just by the luck of the draw. All right, now note that rho equals 0 is the same thing as beta 1 equals 0, because it's, think about it, they're logically equivalent, meaning that when the correlation coefficient is 0, doesn't the slope have to be 0? Doesn't it? And when the slope is 0, doesn't the correlation coefficient have to be 0? So they're the same thing, the same test. And we saw that before. Okay? So, before we do this, what is the sum of squares t? First of all, we're going to be using r squared, and this, look, we want to compute, we're going to get this sum of squares t, and then the model is going to be r squared times the sum of squares t, and the error will be computed as 1 minus r squared times SST. Now we have all the information here, right, to figure out what the sum of squares total is. So get out your iClickers, and I want to see if you can figure it out from this just by thinking about it first. So here I'll put up the problem. And I'll start this. So, which one of these formulas is SST? Remember, here's your definitions of SST, and here's your definition of the standard deviation of our Ys, our homework scores. Here's our definition of that. And here's our definition of the sum of squares total. So how are we going to compute this SST from n and the standard deviation of the Ys? It's just simple algebra there. So choose one of them. All right, I'm going to stop it now, and let's see what you got. Okay, the answer is C, and just about everybody got that. Great. And so let's go back to our document camera, and you can see that when you square this and then multiply by n, that's exactly what you get. So let's go over to our back here and do that. All right? So now we have r squared we can get from little r squared, so we just square that, 0.4 squared, and we get 0.16 there. And our SST, let's write it down, is going to be n, just like you said, times s dy squared. We know n is 107. Now, the only thing is there's two SDs here. Which one is y? Final, because we're trying to predict the final from the homework. So it's 10.3 times 10.3 squared. And that's 11,351.63. So that is our sum of squares total right here. So let's write that in. And now we're going to break this into the two parts. The part that's due to the model, to the line, and that's r squared times that. So it's going to be 0.16 times that, times 1135.63, and that turns out to be 1816.26. So that's our sum of squares model. And then our sum of squares error is 1 minus r squared. So it's 0.84. 1 minus 0.16 times 11,351.63. And I got 9,535.37. So there's our sum of squares model compared to our sum of squares error. Now the F ratio is these divided by their respective degrees of freedom. So remember how we were doing the degrees of freedom. The total degrees of freedom is the usual n minus 1. That's just the deviations around the average here. And so that's n minus 1, right? And then it's broken up into two parts. The sum of squares for the model is the number of parameters in the model, the number of things we're estimating. We're estimating an intercept and a slope. So there's two parameters here. Minus 1, it's p minus 1. We talked about why that was last time. So that's 2 minus 1 is equal to 1. So that's the degrees of freedom for our model. And then the degrees of freedom for the errors is n minus p. So in this case, n is 107 minus 2, so we have 105. And together they add up to 106, which is n minus 1. So it works out. All right. So the next thing that we want to do now, this is really simple. We're in simple regression. So p minus 1 is just 1 here. So, but let's just write it in so we don't forget when we move to multiple regression, when we have to divide by something besides 1. So that's our mean square for the model. And then our mean square for the error is 9,535.37 divided by 105. Okay? And I got 90.813 there. 90.813. All right, so then our ratio of the two is the F ratio. That's our F stat. So F is equal to 1816.26 divided by 90.813. And this turns out to be 20. That's a huge, huge F stat. You probably don't know that yet, but F is sent when the null is true. F has a very nice feature that's very logical. Look at it. It's the ratio of the average sum of the mean square model over the mean square error. And when the null is true, it means the model is worthless. It's no different than error, right? So that ratio, when the null is true, should be 1. The model does no better than the errors. It's all the same. So it's the ratio of the mean square model, which is the strength of the model, to the strength of the errors. The way that F is calculated makes it extremely nice because it says, okay, when the null is true, Model's no better than error. You don't have a model, basically. Your models, you know, you might as well just estimate the y's by the average of y's. The slope's doing nothing when the null is true. So it has that super nice feature that's very, very easy to remember, that when the null is true, f, the mean of the f distribution, is extremely close to 1. And we can look at that in a minute. But now when you see this big an f, you know extreme values of a test statistic, when you see a really big test statistic, really far away from what you'd expect, you know to reject that null, to say, hey, that's a big model. Remember, signal to noise ratio. That's a huge signal to noise ratio. So we've got a signal. We're going to reject that null, and we've got a signal. That's what that is. Now, this square root, you'll often see the square root, the root mean square error, right? Remember, we've talked about that a lot. That's the standard deviation of the errors. The root mean square of the errors. But it's the SD plus, because look how we got it. Here's the sum of squares errors. And then instead of dividing by how many there are, each point contributes an error, right? We divided by n minus 2. So it's divided by 105. And then we take its square root. So let's do that. This is going to be the square root of 90.813, and that's equal to 9.53. So let's just look at, first let's note that this mean square error right here, that's the square root, the root mean square error. Root mean square error. The root of the mean square error here is equal to the standard deviation plus of the errors. And so the standard deviation plus of the errors, in this case, how is it related to the standard deviation of the errors? Well, it's bigger, and it's bigger by what factor? How is it bigger? Well, if we were doing the standard deviation of the errors, we would have divided by 107 here, not 105. So it's bigger by a factor of n over n minus 2. Okay. And so, so in this case, it would be by a factor of the square root of 107 over 105. Now, what do we want to do? We want a conclusion here. So what do we have to, I told you we're going to reject the null. This is huge, but we should find a p-value. So remember, we got an F-statistic. What is our F-stat? Our F-stat, so our F-statistic, you have to look at how many degrees of freedom there are. So remember, an F has 2 sets of degrees of freedom. It's 1 in the numerator and 105 in the denominator here. And our F statistic is equal to 20. So what's our p-value? Well, let's use our p-value calculator and get a p-value. So the p-value is going to be really small, but let's look at it. All right, so we're going to look at the let's go over here to our p-value calculator, and okay. Let's pull up our site, and here's our p-value calculator. So we're looking at the F distribution, and the number of degrees of freedom in the numerator is 1. And the number of degrees of freedom in the denominator is 105, and we've got a test statistic of 20. And so our p-value is very small. Let's look at the picture. Our p-value is extremely small. Now the average, I said, is 1. Let's look what happens if we put if I put a 1, first of all, let's remember what this is. So what is this? 4 zeros. Okay, and if we change it to a percent, it would be 2 zeros, 1967. Let's write that down, 2 zeros before we forget. So let's go back. So our p-value is 0.001967%. That is so tiny. So of course we're going to reject the null. We have extremely reject the null big time. Extremely strong evidence that what? Rho in the population is not, our slope is not equal to 0. We're rejecting that null that it is. And doesn't that make sense? I mean, wouldn't you think that the homework would be correlated with the final? Wouldn't you be surprised if it wasn't? You'd just stop doing homework if it didn't help you, right? Wouldn't you? I mean, we hope it's correlated. All right. Now, let's say we wanted to use our table because the table's confusing with the two sets of degrees of freedom. So using the table, what would we do? So this is using our p-value calculator. Using the table, we'd have to compare what? RF, compare F to what? To the critical value. To the critical value on the F table with those two sets of degrees of freedom at, and will be something, the only one we have in our book is alpha equal to 0.05 because each table, each degree of each significance level would have to have another table, right? Look at this. Let's look at our well, here's how to read the F table right here. And we only have one here. This is all at alpha equals 0. We can just look at the back of the book. It's easier. Okay, so let's just look at that and go to our tables at the back of the book. So it's on page 254. All right, and so you're only given this one, right? And it takes up the whole page here. So what do we have? We have the degrees of freedom in the numerator were 1, and whoa, the degrees of freedom in the denominator, it's off the page here. We have 105. So we really can't even use this table, right? I mean, but can you see that these keep getting smaller here? So ours is 20. It's going to be much, much bigger than the critical value. Okay? Let's look at our other little one. Maybe the little one that let's look at the one that I gave you at the end of the chapter. Maybe that has, yeah, that's a little better. Okay, so we should use this one now because the degrees of freedom, so 107, we could say, well, we're in this column and our degrees of freedom are 107. Usually people go with the more conservative, the smaller sample size, the smaller one, but you could, so if we went with the smaller one, we could say about 4, right? Do you understand that? Because if it passes at degrees of freedom, I mean, the bigger the sample size, isn't it going to be the stronger evidence, the bigger to reject the null? You understand that? So if we went with a smaller sample size, we can't go wrong. It's real conservative. So we could say about 4, okay? And we could do that. So let's go back. And so we would compare 20 is much bigger than 4, so reject the null at 5%. But we know to reject at the p-value is much, much less than 5%. All right, any questions so far? So I just want to ask you, let's say I just gave you that F statistic, 20, and I asked you, what's the T statistic? Would you be able to calculate it from that? What would you do? Anybody? Just raise your hand. Yeah, what would you do? Exactly. You would just take the square root of that, and that would give you the T statistic. So we might as well write that. So note, the T statistic is equal to the square root of the F. So it would be the square root of 20, which is approximately 4.72. Now, do you think we would get the same p-value using this? Should we check? Let's see. If we put in 4.72, or do you think we'll get that? What do you think? Anybody want to say that we would get, what, do you think we're going to get the same p-value or not? Raise your hand and argue one way or the other. What? Exactly. What she said, she knows that chi-squared and chi-squared in F or chi-squared in Z? Oh no, chi-squared and Z are going to be exactly the same. That's a big clue. Chi-squared, and if you take the square root of the chi-squared, you'll get the Z statistic. Now, will you get the same p-value? Do you think? Yes. You'll get it for a two-tailed test. You'll get the same exact p-value for the two-tailed test. But for the one-tailed test, what do you think you're going to get? Just half, just one tail. So you'll just get half the p-value. So let's check it out and see if that's true. Okay? Now, so let's do that. So let's go to our p-value calculator and let's try it. Okay, so here we're going to go to the, so remember this, the 1967. Now we'd have to take the square root of 20. Does anybody have a calculator so we can take it more, I'll move over to the T. And now, how many degrees of freedom for the T? Does anybody know? Do you think, okay, the F had one in the, yeah, well, go ahead. 105. 105. It's this n minus p. Okay, n minus 2. It's going to be the same as the F statistics denominator, the errors, right? And now the t value, the square root of 20, did anybody get that? 4.472. Okay, let's see what we get. Now, if we do two tails, we should get the same thing. So let's compute the p-value. And we get the 4 zeros, 1968 instead of 1967. That's just rounding error. So we get this, look how far out it is. See how far out it is? So it's the same thing. Now look, think about it. If you square all these values, what kind of shape would you get? You're going to get the F. And why? Because if you square everything between -1 and 1 is going to, get smaller. So we'll get more, all the negatives will become positive. And all the values between 0 and -1, when you square them, when you square a half, you get a quarter, they're going to get smaller and going to pile up here. And all the values, the negatives and the positives here, that are, when you square them, they're going to get larger. They're going to extend out this way. So you'll get, let's just look at it, you're going to get the F distribution with degrees of freedom 1, and then we had 105 here, and we had 20, and I just want to show you, if you can picture it, do you see that's what it is? It's just positive because we squared all those values, all the t values, and as I said, they got all bunched up here. You know, when you square a half or a negative half, it becomes a quarter. So a half, that would get smaller and smaller. They get bunched up here. All right? Now, I said, let's look at one more thing. I told you that the F, what did I say was centered at? Do you remember? Let's do an eye clicker, see if you can remember. An eye clicker, see if you can remember what I said the mean of the F distribution was. So let's go to the clicker. That's our next clicker question. And here we go. Okay. When the null is true, the mean of the F statistic is close to what? Okay, I'm just going to give you to 45. All right, let's see what you said. It's close to 1. It should be B. Pretty good. Pretty good. I could see how, okay. I could see why you would think 0. But if it would be 0, that's the mean of the t distribution. Remember? But with the F, it can't be negative. So the mean, let's look at it again. So let's go to, let's get out of here. And let me show you on the p-value calculator here. All right, so first of all, if our F was 1, you might expect, let's see what happens to our p-value. Now, it's not 50%. It's about 31.96%. You'd think if the mean was 1, I should get 50-50. Why don't I? I'm talking about the mean, not the median. Doesn't this give you the median here? The median would be 50-50, right? I'm not saying the median. I'm saying the mean. And since it's a very skewed distribution here, that's the mean is what? Going to be pulled towards the tail, right? It's going to be pulled towards the tail here. So the mean is 1. The median is going to be, and this is 32%, right? That's 31.96%. The median is more about here. That's the mean. Now, as you add degrees of freedom, it's going to start looking really different. Watch. What if I did this? Starts to look more normal. And here, now, it's almost 50%. So the mean and median become the same. So that's the idea here. And so let's go back to any questions on this. And I strongly urge, the best way to understand this is just play around. Just put in different values and look at the curve and just play around with this calculator for all the distributions. That's the way I learn best. And most people do learn best visually. So let's go back to the document camera. And we did all this work here, right? But remember, we didn't figure this all out from scratch like we did here. That would be way too much work. We'd have 107 points. No, we didn't do that. So basically, I gave you, by giving you this R right here, R and N is all you really need. You don't have to do this whole chart, right? Because we didn't do it from scratch. We have R and N. So this helps you understand the structure of analysis of variance if we had to do it from scratch. But since I already gave you the R and the N here, the R here, you can just jump right and use our formula. And you should get the same F statistic. And you can see how our formula really is doing the same thing. So we can say, let's using our formula. So you remember what it is, using F equals, now how are you going to remember it? Okay, so it's going to be R squared over 1 minus R squared, right? And then each one of these is divided by its degrees of freedom. So the numerator is divided by p minus 1, and the denominator is divided by n minus p. But when we simplify, I like this form a lot better because it makes more sense to me. The bigger n is, the stronger the signal is. And the bigger r is, the stronger the signal is. And you can see that in this simplified form. So that is our formula. So in this case, what is it? It's 0.16 over 0.84. And look where that is, 1.6 over 0.84. And these will cancel out, the SSTs. So we just have that over that. And 0.016, that one's divided by 1, and the other one's divided by 105. But when we simplify, we get 105 over 1, which is equal to 20. And that's all we did. Okay? And we should write in right here, we forgot to write in what we got for our p-value. So the p-value is the same. The p-value is equal to the same thing for what? One-sided or two-sided? Two-sided test. It's half it for the one side, just the one tail. Okay, so it's the same. So now let's just do the same thing with the chi-square statistic. All right, should we try that? All right, now with the chi-square statistic, people don't make this table. There's no partitioning like that. It's just, we just use the statistic. So the chi-square is even simpler. It's r squared over 1 minus r squared times n. So you just have 0.16 over 0.84 times 107. We don't have to worry about any degrees of freedom. And as you can see, it's a little bit bigger. We're multiplying by 107 instead of 105. So you get 20.38. Just like the z statistic is a little bit bigger than the t. All right, so let's find the p-value. So are we going to, let's find the p-value. So the p, using the calculator here, this was using calculator, p-value, this is how we got this calculator, let's write. That's how we got that. Let's do the same thing here, and let's use the p-value calculator, and we get the p-value, I'll just write it here, p-value using the calculator. Now, do you think it's going to be smaller or bigger than that? It's going to be different. Remember, you need more evidence to reject the null. Remember with the f and the t, so this is going to be, what do you think? The p-value. Do you think it's going to be bigger or smaller? Then we should, yes, it's going to be smaller. It's going to be smaller, just like the z, when you use the normal curve, you get a smaller p-value. Remember, because the t is fat in the tails, well, the f is fat in the tails too, fatter in the tails in the chi-square. So you can remember that fat in the tails. F and t have fatter tails. So their p-values are going to be bigger because F and T have fatter tails. We'll write that down, but first let's just make sure we're right. So we should get a bigger number than that, and let's check it out, and then we can write that down. All right, so let's go to the here to the calculator again, and now we're going to be looking at the chi-square distribution and the degrees of freedom. Sorry, I said there are no degrees of freedom. Of course there are. There's a degree of freedom, but not depending on your sample size. There's a degree of freedom depending on how many parameters are in your model, but it doesn't depend on your sample size. So our degrees of freedom, how many parameters are in our model, guys? 2. So how many degrees of freedom are we going to have? 1. Exactly the same as the model for the F. It just doesn't have those degrees of freedom depending on your sample size. So there we go with the 1. And now this is bigger. It's 20.38. And let's see what we get. Let's see. So we get a smaller p-value, right? Don't we? We have 3 zeros. We only had, so yeah, we get a smaller p-value. Doesn't, right? Isn't that what we said? The F has a bigger one because F's fat in the tails. Okay, so let's write that down. Now what do we have? We have 3 zeros and 63.49. And then let's do that. So we'll go back to the document camera and write that in. And so the p-value using the calculator is equal to, and we had 3 zeros, and then we had 63.49%. So note F and T are fatter in the tails, fat and tails, so p-values are bigger. See, we only had 2 zeros, and here we have 3. Are bigger than corresponding z, than corresponding chi-squared and z. All right. So let's do the same thing here. Note, sorry, I don't have much room, but we want to note what? We want to do the analogous thing. Note that z is equal to the square root of the chi-squared, which would be equal to the square root of 20.38, which is 4.514, and you're going to get the same, I don't have room to put it here, but what are you going to get? You're going to get the same p-value, that's 3063, what does that even say? 6349. And we'll get that for the two-sided. So it's going to be the same as that. So the p-value for this will be exactly the same p-value for the two-sided. All right? That's 0.006349. All right. I can write it somewhere. Let me just put it underneath. I just need more. I'll just put it right here. So that's, so the p-value for that, so the p-value was equal to 0.0006349% for two-sided alternative. Or what would it be for two-sided alternative? Or here we have room, we can say, or half that, or 6349 divided by 2 for one-sided alternative, one-tailed alternative. All right. So any questions so far on all that? Yes. Well, why don't we do it and I'll show you. Okay? So we'll just go over to the PC. Is everybody finished copying this? Are y'all done copying this? Can I go over to the PC and just show it to you? Okay, so let's just do it. All right. So we'll take the square root of that, 20.38, and we'll do the z. And what I say is I'll get this same thing for the two-sided, but only have it for the one-sided. So let's go to our normal distribution, and we don't have any degrees of freedom, and we have the square root of 20.38, which I said was 4.514, approximately 4.514. Now, if I do the two tails, I should get the same thing. Yep, the 3 zeros, once you multiply by, in percent, 6362. It's a little different just because I did some rounding, but it's essentially the same for the two-sided. But for the one-sided, it's only going to be, if I do the right tail, it's just going to be half of that. You can see. It'll just count the area. The two-sided counts all the area more extreme, beyond negative 4.514 and beyond 4.514. If I just do a one-sided, I could do a right or a left. If I thought it was, let's do a right because we thought it was positive. You see, it's just that divided in two. And it's just looking at half of that. Does that make sense? It's just looking at the area on this side. When we do a two-sided, we think there's a significance. It would be kind of crazy. What would it mean in this case? Going back to our document camera, if we did do a two-sided alternative, it would mean what? Our null is the same, that we think there's no correlation, but it would mean that if we did a two-sided, it means we don't know. When we say the alternative is not equal to, it means we think homework could either help you on the final or hurt you. It does something, but we don't know whether it would help or hurt. That's kind of silly, isn't it? Isn't it kind of a silly hypothesis to do it that way? But it doesn't matter because we can do it this way and just at the end take half the p-value. If we know ahead of time, we say we really just want to look at the positive. So we'll just take half the p-value if you do a chi-square test. Does that make sense? All right, so now let's just look at these from here on. I'm going to let you out early. I said I just want to review some basic, I wrote some, this is a different way of approaching this. It's trying to show you the whole analysis of variance, which we're also going to do when we compare more than two means. Like if we want to see comparing three groups and see if there's any difference between three groups, we're just going to be using this a lot, and I just wanted you to understand it first in the simplest case. So when do we use which one? We have four that all test the same thing, right? So for just our usual, for small n, the t and the f give somewhat more accurate p-values. That's all there is. In the limit, they're going to all be the same. So here's what we've been talking about. The p-value for the chi-square test with 1 degree of freedom is the same as the p-value for the two-tailed z-test. Now, did we include that 1 degree of freedom here? I don't think we did. So we have to do that right here. That's 1 degree of freedom here. And it's not going to come out in the statistic here. It's going to come out on what table we look at to get this. Because we're not going to, the statistic is just what table we're going to look at. What row. All right. And now the p-value for the F, let's look at that. Let's circle that too. Now we're just, notice these are for 1 because we're only comparing, we can only do a z and a t-test when we have 2 parameters, when we have 1 slope there, 2 parameters. We can only do that. That's the only time we can do this, is in simple regression. Simple regression just has 2 parameters. All right? And now let's look here, and here's where I explain. To find the p-value, you can look at either the area of one tail or both tails on the normal curve, depending on what? Depending on whether what? Your alternative, one tail is an inequality, is one-tailed, meaning a greater than or a less than sign, like a greater than sign or a less than sign. That's when you have the one tail, or when then you have the both tails is two-tailed, and that's when the alternative, that says two-tailed, sorry. And that's when you don't specify direction. It could be either bigger than or smaller than. Okay? So here's your statistics. And you know what? Like I gave you a table and asked you to compute them all. I find it easier to do these and then take the square root and then get these rather than vice versa. Because look how easy the chi-squared is. And then you just take the square root of it and you get the z. I just find the calculation easier. Okay? Questions on that? Now let's look at the next page. We're just going to look at these together. There's no more calculations. I just want you to, you know, I say to read these, but who does, right? I wish you did. I wish you did. But I spend a whole lot of time trying to write it into one page here about what this F-statistic is. So I'm going to highlight some important points here because I don't want to read it to you. But I just want you to remember that all significance tests are based on random sampling, that we see some effect in our sample, but the question is, does the effect exist in the whole population, or did we just happen to get a weird sample? We usually don't have the resources to sample the whole population, so we do a significance test instead. What do we assume? That there's no effect, null, no effect in the population, right? If you're testing a drug, it has no effect. You just happen to pick people who are going to get better anyways if you see an effect. Okay, so all significance test does is compares the size of the effect you observed in your sample, compared to the size you typically see due to chance variation when there is no effect. Okay? And now, this is the deal right here. This is the whole point. In other words, a significance test is the statistical answer to the question, did this happen for a reason? I'm not saying what the reason is. I'm just saying, did this happen for a reason? Or is it just due to the luck of the draw? People are generally looking for reasons, right? So people are generally hoping to reject the null and say, hey, we see this for a reason. And then the main idea in all this analysis of variance, whenever you have this linear function, when your model is a linear function of x, the main idea is that you're going to break it into the two parts, right? The parts that's explained by the model, which is the variation that's explained by the regression line, in our case here with simple regression, and the scatter around it. And we're breaking it up into two parts, and that's our ratio, basically. And that's why the F-statistic is so nice, because it's standardized. around 1. So basically when that, and that makes sense to have it standardized. When you have that ratio of signal to noise is 1, well, your signal's no better than your noise, and that's the mean when the null is true. So you want to get a much bigger F statistic than 1, or bigger one, in order to reject the null and say, hey, this is happening for a reason. We don't know what the reason is until we look for confounders and all that, but there's a systematic reason. So that means we can make predictions, right? So that's the idea. And the last thing is our summary, and I want you to read all of it. Oh, and here's when I say, oh, we should definitely go back and highlight this. I'll do it in another color, so you'll pay attention to it. When the null is true, the mean of the F statistic is close to 1. And here's what it actually is. It's the degrees of freedom in the denominator divided by the degrees of freedom in the denominator minus 1. So when n gets larger, that gets closer and closer to 1. Right? So, all right. Now, the last thing, the summary. And let's see, what do I want you to I want you to read this again, of course, but what should you? This is super important. We've talked about this a lot. They can never be negative. And this. But in our next section, we're not going to be able to use Z and T. And now the last thing is the two factors that influence the significance test. The bigger, for all significance tests, the bigger the test stat in absolute value, the smaller the p-value, and the more evidence you have to reject the null. That's for all of them. And there's two factors that affect the test statistic. Here's the two factors: the size of your effect and your sample size. And those are both, when you simplify, those are both in the numerator, right? They give you the strength of the signal. When you simplify, look at those test statistics. Look at them. When you simplify, they're both in the numerator. The strength of your, the difference, but the strength of your observed effect in n, your sample size. So, okay, so that's pretty much it. And we're going to be seeing this over and over and over again. We're going into multiple regression next time. Oh, homework. You don't have any homework due Wednesday because you did it already, and I guess I could I'll just post some for Friday.